When measuring sideband noise in crystals in the previous video, I was using this box. It's the crystal in series with a capacitor, a tuned one in parallel with some fixed capacitance. Here is what I see on the network analyzer. The bandwidth is about 1.5 kilohertz. The Q is 13,500 and the impedance is about 50 ohms. Actually, I expect 50 ohms plus the series resistance of the crystal, but that's not what I see because there are some non-matched wires inside the box, I think. Anyway, the instrument is properly calibrated. This is what I see. The loss through the filter is 1.2 dB, and that's the loss of the series resistance of the crystal. With this setup, I was measuring sideband noise levels. Now I'm going to use a set of these crystals to make a much narrower filter, much higher Q, so I expect to see much more noise in proportion to the Q, but by using several crystals in parallel, I expect noise to be reduced by the square root of the number of crystals. We will see. Here is a prototype to a filter with 10 crystals in parallel. It is the same schematic diagram that I used before, but with a different turns ratio here, and this is now 4 1 ohm resistors in parallel. What I want to achieve is an output voltage at this point of 123 millivolts. That corresponds to 2 dBm power in each crystal, or maybe a little less. So what I have is this, and I look for the bandwidth, and the Q is now 87,000. So this is a reasonable Q to use. I could bring it up, but then the loss through the filter grows, and I might play with that later on. Anyway, this is a reasonable start, and the loss 31.8. That's 4 times dB more loss than before. So I need 4 dB more than before to get the same voltage, which means 17 dBm. That's pretty high, so I will probably use a little less signal than that. And that's also reasonable because looking at the noise evaluation I have made, performance is the first 10 crystals, it's about here. Best is here, and that is 3 dB below the maximum signal. I'm looking at the current through all the crystals now with this current probe, and that did not change what I see in the network analyzer. Not much. There is a small impedance change there, and I have lost from 87 down to 82 on the Q. So it's a small loss due to that probe. Now I'm sending plus 15 dBm into this filter and looking at what comes from the current probe. And it says 30 millivolts peak, but I have set it now to the high scale, so I have 300 milliamps through the crystals. That's 30 milliamps for each one, and before I had the maximum 36. So So 15 dBm into this filter gives the proper operating point for the highest level that I will use on the crystals. I have increased this capacitor by adding two 10 pF capacitors in parallel here, like this. They were going to ground before to get the proper tuning. By moving them there, I get much more signal. So now the loss is only 16 dB, and that makes it easy to measure the sideband noise, hopefully. And I lost Q, so it's now 82,000, so it's still similar. The attenuator is set to 0 now, so the power from this Wenzel oscillator is 12 dBm, and then I split it in two halves, so I'm sending 9 dBm into this filter with 10 crystals and a fairly high Q now. And here is what I see at an offset of 25 Hz down here, and I look what is the level, minus 143 dBc per Hertz. But there are odd phenomena. You can see this thing here, and also here, and here. And they are symmetric versus the carrier, so there are some kind of oscillations in the crystal, I think. And if I knock very gently on the table, you can see all sorts of phenomena coming up. Although, as it happens, they didn't come much in the passband I'm looking at for the moment. Now I reduced the power by 3 dB and made the balancing, of course, on the interferometer that's here. There is a little less noise close to the carrier, and these spurs are weaker. There's no change here, or at least not much. And the noise floor is down. Oops. I look here, while balancing was fairly good. It shows minus 143, but the carrier is 3 dB weaker, so this means 140.5. I take the average of the two. 140.5 dBc per Hertz. And again, if I knock gently on the table, it's much less sensitive to that now. Now I have turned down the carrier by another 3 dB, and I will try the correlation, because it looks like there is a contribution from the two channels. So I look for the correlated spectrum now. The noise floor now is minus 145.5, but there is a 6 dB lower carrier, so that's 139.5. But as you can see here, there is a 2 dB correlation advantage, and I can see here these phenomena are now much weaker, although they are still there. So I don't know really what this means. It seems that the noise is still a problem, and this is with 6 dB on the attenuator to the filter, so it's only 3 dB. Sorry, 6 dB. I have now 9 decibels attenuation. That means I'm sending 0 dBm into the filter. The correlation advantage is 4.9 dB, as you can see here, and the level minus 147, 46.5 and 47.2, so 46.9 say, and then plus 5, so it is minus 151.5. But then there is the 9 dB weaker carrier, so that means 142 point whatever it was, I don't remember him. I'm again at 6 dB attenuation, very good balance on the interferometer. And here I read 146.2, about 146.2, and 3.5 dB for the correlation means 148.7. Well, it's even more, no? 148.7, and then 6 decibels attenuation on the carrier. So that's still about 142 and a little bit better. So that seems to be the limit I can get with this arrangement. So what I found is not so encouraging. 142 minus is here, means here. The line here is a filter that I studied in a previous video. It has 30 crystals, or it had, because I have taken those crystals out and done other things with them. But Q was only 24,000. Now here Q is much higher, so it's more sensitive to what happens in the crystals. And what I wanted was to come down not too far from the 10 megahertz Wenzel oscillator, but I'm only about 4 dB below a previous oscillator that I made with crystals randomly selected, more or less. And that was the case also for this filter. It was just many crystals. I didn't study the noise in them. The output of this filter is a 1 nanofarad capacitor. So the standing wave of the output impedance is infinite almost. I mean about 15 ohms purely capacitive. So I added a 6 dB attenuator and then another 6 dB attenuator in the other leg of the interferometer. And then I have set the level here to 3 dB, well, there's no focus, 3 dB below full power, which means that I'm sending 6 plus 6 dBm into this filter. That is about 9 dB below the maximum that I can have here. And this seems to be optimum. And then I balance the interferometer, of course, and do the calibration. So here is the carrier of the Wenzel oscillator, and it is set to show 0. And then I have a calibration signal from here, which comes at this point. And I have set it to minus 60 dB, which you can see here. minus 59.95. And that signal comes in the interferometer output at 100 kilohertz up in frequency, and the level is here, and it is 60.0, an error of 0.05. I don't worry about that. And so it is now properly calibrated. So I switch off that calibration signal and look for the sideband noise. And the noise floor I see now, it is minus 139, but there is a 5 dB correlation advantage, means minus 143. But there is a small difference. If I knock gently on the table now, the sidebands I see here at 20 Hz, they are weaker than before. And generally things look a little bit more stable. And I cannot explain it, but ideally things should be matched reasonably well to 50 ohms. The bandwidth of the measurement is fairly large. I will make it narrower by first expanding the third FFT, and then I can make the filter bandwidth narrower, something like that. And now evaluation is much slower, so I will have to wait some time. I'm still looking at 25 Hz offset with the much narrower filter. And here is the main spectrum. And I look for the correlation. The correlation advantage is 4.7 dB. And the noise floor here is minus 138.9, the average between these two. 38.9 plus 4.7. And that makes minus 143.6. Now, this what I have done is a bit inconvenient because the signal levels are low and I cannot measure at larger separations than this because I get into the noise floor of the test system. I still have this 6 dB attenuator on the output, and I'm measuring this filter now in the reverse direction, so I can see that the output impedance is 32 ohms, not too close to 50, and that the Q is 83,000. And now I replaced that output capacitor with a 47 ohm resistor. And then, according to the network analyzer, I have 44 ohms, maybe some little error on calibration. I think it is a 1% resistor. And I press bandwidth to see what happened with Q and loss. It was 84,022.2 dB. And now it is 67,000, which is much less, and 19 dB. So I have to reduce the capacitors. But before that, remove this attenuator, of course. So the coupling capacitor is reduced from 24 to 10 pF, and the load resistor, I had to put 10 ohms in series, so that is now 57 ohms. Then this is what I see. The impedance is nicely 50 ohms, 51, and the Q is almost 81,000. so it is nearly as high as before. And the loss through this is now 18.7 dB, so it's a little bit better than before. And the impedance is significantly better. I don't expect any change, but I will have a look for that. Well, now I see minus 140 here, and the correlation advantage is 2, means minus 142. So there is a small degradation for unknown reasons, but I can see these noise sidebands that come from the crystals are stronger now. And you can see them here, also in the waterfall. These are noise sidebands. Here is something that looks like a sine wave, and here is 50 Hertz, which is narrow, of course. And if I knock on the table a little, you can see these sidebands come up much stronger. And I have to wait to see them here because things run very slowly now. I am now running full power, and I make sure that calibration is correct. Here is the carrier from the vent cell showing 0, and here is the calibration signal. Oops. Showing something much less. I have to increase it. Showing now minus 59.985. So it's 60 dB below the vent cell, the carrier. So I will adjust the linear calibration so it here will also show minus 60. That is a 3 dB difference. Like this. So I will look at the sideband noise again. And now I see here minus 142.2 with a 1.3 dB correlation advantage. 142.3, 143.7. It's almost minus 144 dBc per hertz. It's like before, but this is at the full power. This is 12.5 hertz, and I can see the noise floor is no longer flat within the filter, so I have to make the filter narrower. Here the correlation advantage is smaller, 0.9 dB. The noise floor is not quite stable, but on the average from here to here it is minus 138.4, and this is maybe 0.8 on the average. And here is 40 Hertz offset. I see minus 143.4 and 2.5 dB correlation advantage. Here are the points I got now. They fall nicely on a straight line, but the slope is different from the line I had with the 30 crystal filter. So it's better at very close range, but not so good at a wider range. I don't know why. I have replaced those 10 crystals with 10 other ones, those that passed the sideband noise test. And I find Q is a little bit lower. You can see the old curve here. and the difference is small, but this was I think 82 and now it's 76,000. And it's obvious if I go for the impedance here, it is now 63 ohms, but if I look at the previous, which I have in memory, you can see that was 51 ohms. So the resistance through the crystals is a little bit higher, and that gives a lower Q and a higher impedance. But these differences are fairly small. I will look at the noise properties of the filter now. Here is what I see with the second group of 10 crystals. There is now a spur at 25 Hz offset. I guess it's because it's starting to get daytime now. The noise I see is minus 139.7, and the correlation advantage is small. And this spur is going up and down and may have something to do with it, but not much. I can see that from how the curves behave on the sides here. So I have about minus 140 dBc per hertz. That's clearly not quite as good as I had with these crystals. I have reduced the carrier by 3 decibels, and it seems that this spur is much weaker. So maybe it's because of the crystals some odd way. Anyway, the noise here is not 3 decibels lower. It's more like 1.5 or something. So reducing power didn't do any dramatic improvement. I have now connected all the crystals in parallel. And what I see here is not what I expected. The level at 25 Hz is minus 134. And there are these noise spurs. I guess they originate in the crystal. So I will look a little bit closer at this to see if I can understand something. I have placed those 20 crystals in this box and made a mechanically stable design this time. It's a different schematic diagram, like this. Uh, 20 crystals parallel to 300 pf to get the resonance at the right place, 18 pf coupling capacitors to get the suitable coupling, then 68 ohms to ground to make the impedance 50 ohm almost resistive here and here, and this inductor about 40 microhenries to balance the capacitive coupling from here to here to get a symmetric and nice filter. I have the oscilloscope probe connected here on the crystal, and this is what I see. It says 26 volts peak to peak. Now, as it turns out, when I remove the probe, I see on the balancing of the interferometer that the signal becomes about half a dB stronger. So it's more like 28 volts peak to peak. It goes a little bit above 26 here, but it's not perfectly stable, the readout of the oscilloscope. I don't know why. Anyway, 28 volts peak to peak. That's suitable. To achieve this, I have added amplifiers. There are two 6 dB amplifiers there. So there is 12 dB more power. Means 9 that I had before plus 12. So it's 21 dBm into the box. When making an oscillator around this filter, I will not have those resistors, so it will be more favorable. Since I found previously that 36 milliamps peak to peak would give 38 volts peak to peak across the crystals, I conclude that now with 28 volts the current is 26 milliamps and the power 0.96 milliwatts. That's close to 0 dBm. And that is with 0 on the attenuator. I verify calibration. This is the Perseus. And I read 0.05 dB. That's close enough to 0. This is the vents of the main carrier that I'm looking for sideband noise around. When I switch on this one to inject a weaker signal, it comes here. And I set it to minus 17 dB before. Now it is minus 69.95. So it is minus 69.9. So I can decrease it by 0.1 dB. Like that. Minus 70.05, and this was minus 0.05. So now this one is 70 decibels below the main carrier. And that comes here at 10 megahertz plus 100 hertz. And I want to see minus 70 here, and I have minus 69.6, so I have to change a little bit. So now calibration is okay. First I look at 25 Hertz offset here, or you can see here. This is memory from when I adjusted the interferometer. First, we note that the spurs at 50 Hz and 100 Hz and 150 Hz, they are fairly strong. They are sharp lines, as you can see on the 50 Hz spur here. The noise floor increases as the balancing becomes less good. But I can look here, and then I find that the noise is at minus 146.9, sort of average between those two. And there is no correlation advantage. Well, maybe 0.2 dB. So minus 147 at 25 Hertz. I have a problem with thermal drift, so I have to readjust the phase. That's here. And that, of course, creates a noise burst. And there is a delay through the system because of the very large FFT3 transforms. So here is that readjustment, and you can see it here. And I expect the noise to be a little bit lower than it was before. Well, we will see. Maybe not. And the thermal drift goes on. It's getting colder outside, and it reaches inside also. Well, I will accept this as the noise floor, 143.3 or maybe 143.4. This is 40 Hertz offset. I have a correlation advantage of a couple of tenths of a dB, and the S-meter reading is minus 149.4. So let that make 149.6 then. Here is 120 Hertz. I don't see the noise anymore. I will have to change here the gain. Let's make it 5 instead. And then you can see we have noise that is clearly stronger there than there. The correlation advantage is 1 dB, and the readout is minus 154.1. These points follow a straight line. Here, it doesn't have exactly the same slope as I had before with 10 crystals at some different power level that I don't remember, or actually maybe didn't measure. Well, yes I did, but I don't care about that. Now I have this, and that is 20x crystals and 0 dB with the current notation. I have turned down the power level by 3 dB. I'm looking at an offset of 120 Hertz. And I have a correlation advantage of 1.5 dB. And the level I see here, minus 152.5. That is 154, comes here, about 1 dB worse than I had at 3 dB higher power. We'll see what happens at closer separations. Here is 40 Hertz, well, here, and correlation is very small, so I get minus 147. Here is 25 Hertz offset, and the noise is 144.4. And here is 12.5 Hertz, and noise is minus 141 dBc per Hertz. At minus 3 dB, the latest points, the noise level is a little bit higher than it was at 0 dB. It's this line, and the slope is a little bit steeper. So the difference is larger here than it is down here. So this is a little bit surprising, as everything is with these crystal experiments. I have again set the attenuator to 0, and now I'm looking at the long time development of the sideband noise. And it's obvious from here, and here I have it quantified, and the best is about like that. It's now minus 145 something, and worst case here minus 140. So it's a variation with 5 dB, and it seems that I was at a very lucky position when I measured this the first time. I will allow this to run some more to see for a longer period of time. So I repeated this time. It looks like this. Here is a readjustment of the interferometer balancing, and it is this peak here. So it's more stable now. This region I read minus 146, and if I take the entire range, well, including readjustment, I see 145.4. And the balancing is good now, but I will just do like this, and that's what happened. So it jumps up and down when I knock on the box. So this is where I knocked on the box and rebalanced, and after that the curve looks a little bit more stable, but not much, and now it shows 146.2 on the average. I'm still looking at 25 Hertz offset. The noise floor seems a little bit more stable now. What you see here is when I adjusted the interferometer, as well as there. Corresponds to this event and that event. Now this was spontaneous, and some other things you can see here. That's reflected in the not quite white noise-like curve you see here. But I take this now as the average at 25 Hertz, minus 146.7, and there is a suggestion of a correlation advantage here. That's because the interferometer balance is no longer perfect. So if I retune that like this, or maybe even so, now it's perfectly balanced. Then I have to clear alternate Z like that and wait for 200 spectra, because I have 200 here. So I need to collect 200 to get the white track at the proper position. And it was here, and I have no means of how to remember this position, but if I just clear the screen, it was this. I can recognize the curve. I should expect now the correlation advantage to go to 0, and to gain that, was it 0.4 dB lower here. But already now the balancing is no longer perfect. So this is one of the difficulties with this setup. The oscillators I'm using for the direct conversion receiver are not good enough. So I need to have a very good balancing to get rid of the noise from them, and that is not compatible with the temperature stability of things. So although, and I have now 0.4 here, so this is a problem, and I will demonstrate that by deliberately misbalancing like that. This is a big unbalance, and I have to check that I don't saturate anything. No, there is 20 dB up to saturation of the AD converters. I did clear the correlation, and now I see 2.4 dB, and if I evaluate here, I see 144 or 145. There is a 1.5 dB difference, because that's the difference between the two oscillators I'm using for the direct conversion, and 2.6. It means if I read here, I should read about 2.6 dB better. So, and that should be some kind of average from 146.8 to 145.3. That's 1.5. 146.9 to 144. That's about 3 dB. So this is how this thing works, and I have an accuracy problem because of the stability. But it's not a major problem. You can see here how the noise has gone up, but it was a strong unbalance I made. So I restore. That was the phase, and here is the amplitude, and I need both hands to do this right, but I have only one because the camera is in the other hand. But now balance is good, and you can see how rapidly it doesn't stay so good. That was a jump on the, probably a frequency, a jump in the crystal probably. Because the interferometer is very stable. Here we have some things, instabilities, and of course they are seen as noise here. With some time delay. I have now replaced this crystal filter with this attenuator, set it to 18 dB, and then I look at the screen here. So this is the interferometer itself, plus that attenuator and the other attenuator in the other leg of the interferometer. Here I read minus 158. So it's clear the noise that I was seeing here actually came from the crystal filter and not from the other attenuator or something else in the other leg of the interferometer. I have again connected the filter to the spectrum and to the network analyzer, and I save what I had on the screen to look at it later when I have changed some components in the box. I will replace this one, glass encapsulated ceramic capacitor, by parallel 2 times 10 pf polystyrene. Going from 18 pf to 20 pf makes the loss a little bit smaller. This is data now, and this is what I had before. The Q is a little bit lower, not much, but to some extent, because the 10% increase of coupling. Here is the new, what I have, and memory. Here is the previous. It differs by about half a dB, 17 to 17.4. If I go for marker, Q here is 96,100. Display and on data, and back to marker search. 96,100 before, and now 93,300. So I have lost 3,000 out of 90,000. That's not much. Well, the capacitor replacement seems to have made a change. I am at 25 Hertz, and here is the S-meter graph. This is the calibration, should be minus 70, and this is the 2 upper lines, and calibration was here. And the noise floor now, minus 147.3, and it looks stable. Interesting. Here is the noise at 3 dB attenuation. 145.2. Six dB attenuation now, and the noise I see, 25 Hertz from the carrier, is 143.5. So it degrades as the signal becomes weaker. Now attenuation is 9 dB. And here is the S-meter graph. And it reads minus 141.9. So it still degrades. Here is what I had at minus 6 dB. It's only about 1 dB higher. Of course, calibration is not correct here, but it is correct here. 141.9. And now 12 dB. And I go from here to here, because balancing is degrading slowly. But what I see is minus 140.3. So this is discouraging. Minus 47 at the highest power level, and it degrades gradually. So 12 dB less power is 7 dB worse noise with respect to the carrier. It means that the noise stays nearly constant while the carrier is brought down. So using many crystals in order to bring down noise seems to be not a good idea. It is helpful to bring down the wideband noise at wide separations because it lowers the impedance for the amplifier and therefore it gives less noise, given that the signal level is the same and the lower impedance means less thermal noise and also less noise from the active device itself. So this could be good for oscillators if you are worried about the sideband noise at separations of 10 kHz or something above that perhaps, as I have shown in previous videos with many crystals in the oscillators, those that I'm using now. But they are not particularly good at a close range. And it doesn't seem that I could do something better with these crystals. I have now placed a phase modulator directly after the filter and balanced the interferometer, but not quite. So there is some unbalance. Means I have a carrier and I have the flat filter with the Gaussian error function as fall off, so the spectrum here looks a bit ugly. But it's good for the transformation to baseband. Here is the center of the carrier, and there is a notch at the center frequency, and I'm running in coherent mode 2. This means that one channel goes to the loudspeaker is AM modulation and the other channel is FM modulation with respect to this carrier. Of course it depends on the phase of the carrier what I see. So I use this signal generator to inject a low frequency signal with known modulation type. Right now you can see 83 Hz. Green and red are equally strong. That's because the phase. So I have to turn the phase knob of the interferometer. Sorry. Looking for the minimum, which is here. So right at the minimum, the carrier should be in phase. And as you see, the injected signal is strong in red here. The double peak here is an artifact of the way the carrier is produced. What is interesting is two things. At very low frequencies, below 20 Hz, it's mainly red, means frequency modulation or phase modulation. But at higher offsets, it's about similar amounts of phase and amplitude modulation. I have modified now the filter with 20 crystals in parallel, like this. 47 pf instead of 20 pf. I added an inductor to get 50 ohms and increased this resistor. And I had to reduce this capacitor a little bit. So it doesn't look much different. But here is what I see in the network analyzer. 47 ohms. And the information here is from the previous configuration. That's what I have in memory. The loss 17 dB and Q 96,000. Now, with the new component values, marker, search, Q is 3 times lower and the loss is 4.8 dB. And it's with the new configuration. I have 47 ohms. Previously it was 54 ohms. But you see the variation with frequency is now, display. It varies much more with the frequency because it couples much more to the crystals. I now have 28 volts peak to peak across the crystals, and I have retuned to have maximum with the probe loading the crystals. And to get this I have to attenuate by 2 dB when both amplifiers are amplifying the signal from the Wenzel oscillator. This means with the new configuration the same voltage across the crystal, 2 dB less power, and the Q is 3 times lower. And what does that do with the sideband noise? That's the big question. I'm looking at 25 Hz offset, and the main waterfall looks like this. And if I read the noise, it tells me minus 157 dBc per hertz. And balancing is not perfect. It has been running for a while now, the system. So I clear the correlation to see how much that unbalance influences this measurement. When balancing is perfect, there is no correlation advantage, but now with some unbalance there is, probably. I need to collect 100 averages, because that's the number of samples in the white spectrum. So that's here. And there is half a dB of change in the noise floor because of the unbalance. So I turn the balancing knob. That was phase. And here is amplitude. And I should have 2 hands to do this. 3 hands, sorry. Well, this is good enough. And then I have to wait a couple of minutes to get the improved noise floor here, which will be associated with no correlation advantage here. Here is when I made the balancing. You can see the white trace is a little bit narrower here as compared to here. Correlation advantage is now 0.3, 0.2, but I have to look at the statistics. It goes up and down around a much smaller value. I can see on the noise trace that it looks more red than blue, means the 2 channels are on the same spot, and the reds are the ones that are written after the blue. So here, when the channels are different, you see both colors. Here it's only one color. And I expect the noise floor to be 0.2 dB lower or something. And it isn't. Well, I'm now at 12.5 Hertz. And here is when I adjusted the balancing the latest time. So at 12.5 I have minus 153.6, and at 25 I had minus 157.1, and of course the decimals are uncertain. Here is 48 Hertz, just below the 50 Hertz modulation stub from magnetic fields on the crystals. The noise floor is a little unstable, but on the average minus 159.9. Here is 98 Hertz, just below the 100 Hertz modulation spur, and the noise floor is very nearly the same, 160.7. And here is minus 97 on the 100 Hertz spur on the other side, and the noise floor minus 160.9. Very close, although it looks a little bit different from the screen. This is minus 200 Hertz. Minus 162.7. I have made the main waterfall a bit wider, and now I'm looking at plus 200 Hertz. And here is the noise floor. Minus 156, minus 160.9. I have expanded the scale, and it's clear now that the filter is slightly mistuned. So maximum is somewhere around here, and that's why I get the difference between the two sides. So I take the average of these two as the properties of the filter. Here is 1 kilohertz. I have increased the bandwidth significantly, and this runs much faster, although in bursts, as you can see. And if I read it here, I find minus 164.5. I can look at the correlation spectrum here, and I see 1 kilohertz below, that's here. It's about 1 dB below what I see here. So that's minus 165.5. And then the noise floor looks flat at wider separations. I will expand the window to the full width. So I see now that the noise at 4 kilohertz, it's now almost flat, and it's the same on both sides. And it's 1.5 dB below this point, roughly. So I say minus 166. And the correlation is bad. So that's why the white track is fairly high above the correlation spectrum. But the correlation spectra is what is valid here. I have replaced the filter with a good attenuator set to 5 dB and adjusted the balancing of the interferometer. And here is what you can see. The frequency doesn't matter anymore. What I read here is minus 175. And if I change the scale, remember where we were, the flat noise floor was around 28 here. And I should look at the green trace. The white is mostly the power of the local oscillators I'm using for the direct conversion receiver. But the noise now is about 22 decibels below the flat 4 floor I had. So it's in the order of minus 186. So the flat noise floor I saw from the filter does originate in the filter, and I don't know the reason for that. It could be the crystals, but it could be a capacitor or something else. Maybe poor connection somewhere or something. Anyway, I'm satisfied with this little table. I will look at it in a diagram. So what I have is a curve like this. And the reasons why it flattens out is maybe something I don't need when making an oscillator of this. Q is not very high, it's only 30,000. But noise is now very low, far below what I see from the Wenzel oscillator. Now, how that affects the oscillator with the very low Q that it has now, I don't know. The Wenzel uses a crystal with a Q of about 1 million. And now I have 30,000. There's a big difference.